There are 8 million YouTube talks online, but if you want to really experience it, you have to come in person. It's great. I mean, you'll just meet such cool people.
Hello, everyone. I'm Pejman. Happy Friday. I know that today is the last day of CppCon. So for those who are watching us in the future, I just want to say that we're all exhausted and want to go home. So I'll try to make this talk worthwhile of your time. So thanks for being here. The title of my talk is about building an extensible type serialization system using partial template specialization. When I started preparing for this talk, I realized that it would be doing injustice to the new features of the language if I just cover partial template specialization. So I decided to to prepare this talk in a way that would cover all the approaches that we have for designing extension points in C++. In fact, if I could, change the title, I would change it to a practical review of approaches to designing extension points. This has two benefits. One is that it de-emphasizes the usage of partial template specialization a little bit. The second is that it de-emphasizes building a serialization library, because when we are talking about extension points, we are not necessarily just limiting ourselves to designing libraries that are for serialization. Hashing functions and servers and everything else, when we create libraries, we need to ask ourselves if we want to build it in a way that extends the functionality to users and consumers of our library. So this talk will not be just about the partial template specialization. It would not be a deep dive into template metaprogramming either. It would just be practical, review of everything that we can do to extend our libraries in an elegant way. So what I want you to take away from this talk is the excitement about the new and upcoming features for the language, and also just the mindset of how do you design a library that enables intuitive developer experience for its consumers. And there's a lot of ground to cover here, so ask that you keep your questions for the end of this talk. But if there's something that you cannot wait to ask, please raise your hand and I'll be happy to answer. Let's start with me. So the inspiration of this talk came from my work at Canon Medical Informatics, where I was working for the last 4 years. At Canon, we were building a software for visualization of MRI and CT scan datasets. The picture you see on the right side of the screen is a visual output of our software. It's just one of the visual outputs. But you can imagine that to achieve this, we needed to build a software with millions of lines of code. So doing it in a way that is basically building this software in a way that makes sure that it's suitable for medical uses is challenging. It was particularly challenging when we decided to rewrite a critical component of this mission-critical system, which was 500,000 lines of code. And it wasn't easy, because every time we made changes to our code, we had to have a way of making sure that it doesn't have unintended side effects. So we needed to come up with a system to test our changes in an automated way. Our first try was to basically create a test infrastructure that would call our data pipeline or whatever we were building twice. Once with the legacy version that we were trying to replace, and once for this new version. So then we ended up with two basically outputs of these systems in memory, so we could compare them. In fact, when we designed the system, we decided to derive these outputs from a simple base class, but then all because we wanted to make it easier to compare the outputs. But at the same time, it wasn't easy because we had to write a lot of code to compare these outputs together. Plus, the disadvantage of this approach was that the test infrastructure was extremely clunky. We were calling this old legacy system every time we were running this test, but the old system didn't change in behavior. It was the same. So the time that it took for us to run the test for the old system was the time wasted. So we improved this by creating a different, basically, test infrastructure that calls a single version of our software with multiple test cases. In our case, it was MRI and CT scan data sets. And every time that we have this output, we would serialize the output into files. So then we could compare basically the new version of our software and how it behaves against a previous version that is stored in a file. But this too had some issues. Managing files in general is just very difficult, especially when it is at a scale that we wanted. So the test system was extremely clunky, and the serialization that we were using to serialize our data into binary format, right into these files, was also specific to our use case. So if we were done with this project, we had to throw away all of the code that we had written for comparison and file management and everything else. So this got me thinking: is there a way that we can write a system that serializes binary format and manages and all the results and compares the results against the old ones in a way that doesn't require files? So that means we would have a remote compute resource somewhere either in our infrastructure or out in the cloud, that when we run our test, then we would basically serialize all the data and submit to it. But this meant that we need to build a serialization system that is generic enough, that is applicable to all the possible use cases out there. And this is basically the reason I came up with this talk and the serialization library. So imagine this very simple case where we have a find student function that takes a username and provides some very basic information about them. Now, the solution C that I came up with requires writing this code as our test code, where you would basically create this workflow and then call your code under test, in this case, our find student, with some test case that comes from the outside. It's given as a parameter to our function, to our workflow. And then we can describe the behavior and performance of our code under test by capturing values of variables and runtime of functions. So I want you to focus on the CppCon function calls. These are the function calls that we are going to emphasize today, because this function takes as input one parameter, which is the name of the data point that we are capturing, and then the separate parameter, which is the actual data point. Now, this data point can have any type. The goal in this talk is to come up with ways that we can actually serialize all these arbitrary data types. Now, we have just a few requirements for our design. Our design needs to be intuitive and give developer experience that would motivate people to actually use this library. Of course, it needs to support basic data types so that consumers of the library don't need to spend the time basically redefining all these basic data sets. But at the same time, it should be extensible enough so that our consumers can have a way of passing and using their own data structures and types as they do with basic data types like integers and strings. So these are the goals that we are going to evaluate different techniques against. Now, let's start with a very basic techniques to extend the functionality of a given library. We all know function overloading. Function overloading enables us to, define basically separate handling for specific data types. Now, function overloading is great, but for our case, where we want someone to pass us a vector of dates and not worry about how it should be handled, would be a problem, because then we need a separate overload for a vector of date. Now, we're going to come back to function overloading, but right now we are sure that we cannot just use function overloading for our case. A separate a separate technique for adding extensibility to our library is by offering callbacks. Now, callbacks are great because then we can basically have our users define what we should run when they're calling our library. But at the same time, they seem to be, making the user interface a lot clunkier if we are only going to use callbacks. So now you might be wondering, maybe we should use polymorphism or inheritance, where we define some serialized method that is pure virtual or an interface, and then we basically ask everyone who is trying to serialize their data types to inherit from this or implement this interface. The problem here is that this is asking for too much, especially for C++. No one is going to use our library if we ask them to, derive from this interface and implement this function. We might get away with this approach in other languages. In Java, there is this JSON library, which is very well designed, and its way of usage, it requires basically using a JSON serializer and implementing that interface. So now we can pass our JSON serializer type to a register type adapter every time that we want to serialize something to JSON. The problem with this approach is that so this requires that we register these type adapters at runtime. Now, Java people might be okay with this approach, but we are using C++, which has inherent capabilities to mitigate this, to make sure that we don't have to tell at runtime, look up basically how we want to serialize a given data type. We want to do it all at compile time so that it's efficient when we are actually trying to serialize a given unknown type or external type. So again, back to our simple example. Let's just imagine that we have a toString method. What I want to show here is existing approaches that we have in our well-known C++ libraries for designing extension points. The most famous that I could think of is output stream. When we want to print some data type of an external type using output streams, then we can basically create an operator overload and then use our type just like any other type. We have a similar thing with QDataStream in Qt library when we have basically function overloads for simple data types and also for native Q classes like QObject. But at the same time, we can extend this the set of supported types to any data type by using overloading, operator overloading. Another example is boost serialization, where we can open up the boost serialization namespace, define our own serialized function, and make sure that once we compile our code, then from then on, if we are using a date, then boost serialization knows how to handle that. Of course, there is an alternative approach that we can take with this library. We can create a basically member function and make it so that it can use our private data types without any issue. And lastly, as an example, I would present a standard format, which was added in C++20, and it allows extending the functionality of the formatter by specializing the format function for the formatted class. So now we all know what function template specialization is. As a refresher, here is how, when we talk about template specialization, how the language allows us to handle different types. We have basically a specialization here for a date object, where every time that after the name lookup, when the compiler is trying to resolve the data type, and it can find the overloads for our function. Now, of course, we can make it easier with new language facilities that was added recently, but at the same time, the function template specialization is the same. We also have class template specialization, where we can explicitly specialize a given data type. Now, we can go further and basically, so class template specialization is used for, say, standard hash. But this has problems of its own, because again, for us, we want to make sure that any container or a map or any derived basically type of our external type can be automatically handled. So the way that we can achieve this is through partial template specialization, where we define basically multiple type parameters, and then we can basically partially specialize some of those type parameters. In this case, I'm specializing the date parameter as the second type, which allows me to actually make sure that every time that I use date as the second parameter when I call a printer, it would use this specialization instead of the default, the primary template. Now, we use partial template specialization already when we use enableIf and sphene. Like in this case, here is one possible implementation of sphene that actually specializes the first template parameter, so that every time it's true, then the second basically our specialization gets called. Now, because this specialization has a type, then we can access this type in our specialization. Here is basically the same thing that we achieved with function template specialization through using enableIf, where we are basically asking our users to define this second specialization and say, if you are passing me date, then I'm going to do this instead. Now, the way it works is that when the compiler finds a type, it would basically try to pass this type to our template type T in our isSame, and it checks if isSame is returning false or true, right? Now we take this true. If we are passing a date, then the evaluation would be true, and therefore our enableIf struct would have a type. And therefore, when we are asking for a type, this kind of evaluates without any issue. But imagine if you are passing now a data type that is not a date. In that case, the evaluation would be false, and therefore our enableIf construct wouldn't have a type alias as a member. And therefore, when we are asking for a type, the compiler fails to evaluate this or substitute our expression. Now, we have this facility in our language baked in that enables compilers or asks the compilers to make sure that any failure in our substitution is not going to be treated as an error, that it would gracefully handle cases where the partial template specialization is no longer valid. So because we are using class templates here, at runtime, if we don't have any date, then there is no instantiation of this function anyway. Now, of course, the code snippet that I was showing you was a little clunky. We can clean that up a little bit using enable if t and say is same v. So now we get a better code snippet, but at the same time, it still feels clunky. It's not what you would consider an intuitive developer experience if every time I need to do this. So let's put that aside. We know that maybe partial template specialization is not very great at developer experience, but let's just say if we wanted to do this using partial template specialization, how would we go about doing it? Now, this is the same check function that I was showing you earlier in this talk. And you see here that I'm passing some different types as the second parameter. Now, if you wanted to use partial template specialization as a technique to serialize all these random data types, then we can basically create a perfect forwarding to kind of pass these values as they are to our serializer function. Now, here I am using the serializer to serialize all these data types. So now I can focus on how do I want to handle these types, which in this case are the value type parameter. Here is one possible use case as our library users would see. If they want to specialize date now, they can do that by basically writing this code, which creates an object. They would just basically populate it with any data points that we know how to handle, and they would return it. In fact, this is the best that we can do with partial template specialization. Of course, we can change how we are designing our return value and make this fancier. But at the end of the day, that's what we expect our users to do. Now, I say this because I want to get back to how we can actually expect less and make our users happy when they're using our library. Now, imagine if this date specialization is not provided, is not visible to the compiler, then the compiler, when it encounters a date object, doesn't know how to handle it. And therefore, it basically shows all this compile time error that is not easy to read because templates and template metaprogramming is just known for all those long and undecipherable compile time errors. But we can mitigate that a little bit by making sure that basically as a fallback mechanism, any type that we don't know how to handle would basically be treated as a compile time error with an error message that we want. Now, in this case, we say if there is any type that we don't know how to handle through our partial template specializations that falls into our primary template, then unless it is already the generic value, which is our return type, then we want to basically make the compiler stop proceeding and treat it as a compile time error. Now, our objective from now on is to create these partial template specializations for our known types and then have a way of basically making sure that our users don't need to define them when they are using our library. Now, this is perhaps one slide that is very different if someone else was presenting here, because depending on our use case, the types that we want to treat as our native types would be completely different. For the library that I was telling you about, we want to support binary data, large text. What if someone passes a file system path? Then we want to basically handle the path and use the binary data for it. So, however, because we are not necessarily trying to implement a serialization library here, let's just content ourselves with the set of types that you see on the right side. Now, we can either use a std variant if we can, or in the very basic case, we can just use a union and a type. Now, we can create a type wrapper to make sure that our booleans and numbers would essentially have a way of be representable when through a simple type interface. Now, by defining that, then we can say, here is our specialization for a Boolean value. Now, notice that we are writing 4 lines of code just to explain how a Boolean value, a value of a Boolean type should be handled. But we can even add more code and say, we want to basically say our enable if statement there is only taking a type instead of just having all this, kind of logic squeezed into that, the input for our enable if. We would just create a type alias, or in this case, a const variable. Now, we can extend this functionality to all the other types. In this case, our numeric types, we want to handle our signed integers separately, so we can create a partial template specialization for it. And then say that, one possible way of implementing this is to say, our isNumber sign type alias is always false unless it is an integral sign type that is not a Boolean. Notice the not a Boolean here because partial template specializations have a limitation in that they cannot overlap with each other. They are mutually exclusive. So that might feel, that in here it's just not is same. But when we are creating, multiple of them and many of them, then it kind of comes in our way. It doesn't allow us to express our intentions very well. Now, in here, we can somewhat help, again, with the way that we are expressing our intent by using other facilities like conjunction, negation, and disjunction. Here, I am basically proposing a dummy partial template specialization for a string. Now, of course, we know, a better way of handling this is so that we can handle all types of a string, not just basic string car. How about arrays? Well, you might see in the wild something like this, which is from an actual library that says anything is an array if it is, from array or a set or a vector. Now, how many of these types do we have? What do we want to accomplish? If our intention here is just to check if something is a container, then writing all this code is just not the right way of doing it. Now, we can clean up this a little bit by creating a type alias for is a specialization, because our containers are, basically our templates themselves. Then we can basically check if they are, if a given type is a specialization of these, templates. But again, we have the same problems. How many of these container types do we have in the language? What do we want to accomplish? If we just want to know something is a container, so we can just loop over it and iterate, find the elements, and then serialize them separately. Doing this is against our intention. It doesn't express that very well. Here is another code that is actual real-world code from an open source project. It basically checks for a begin and an end of a given type, and if the begin and an end are there, it would assume that it is an iterable. Now, if you were to use this for basically expressing our intention with is array type alias, then we can say anything is an is array if it is iterable but is not a string. Notice not a string again, because we don't want overlap between our types, our specialization filters. Here is basically the way that we can now write some partial template specialization for our container-like types. We would loop over them and then basically call serializer again for each element of our container. Now, we can go on and on. Here is basically some specialization for a pair, because say if you pass a map, then we end up with pair as elements. So we need to know how to specialize them. The point here is not to show you elegant-looking partial template specialization. My point here is that this cannot scale very well. That there are just too many types that make it extremely difficult for us to express our intentions. And there are language facilities that help us better express those intents. Let's take concepts. Again, we are not going to go do a deep dive, but just imagine how easier it would be if you use concepts instead. Of course, concepts are introduced in C++20, so this may not be relevant for everyone who is implementing a serialization library. In particular, that serialization library I told you about, which is about testing legacy code, cannot use concept as the only means of extending its type support. But I assume that you know the basics. Here is one example where we are basically creating a simple concept using a requires expression that would check if a given type has a toString member function. Now, notice that I am still using templates here, but at the same time, using concepts as just constraint allows me to have basically a better way of expressing my intentions. Now I can say if there is a type that has a toString method, then I want to basically use this last specialization or overload for it. But if I don't know, or if my type doesn't have a toString, then I fall back to my default overload. Now we can take a step back and reconsider our entire approach. Remember that perfect forwarding way of serializing things? Now I can use basically a simple serialized call instead of using partial template, basically instantiating my template class. Now, because we are only using template overload, overload, so I can just use a simple way of saying, here is how I want to serialize a null pointer or a Boolean. What about numeric values, the arithmetics? We can say, all right, I want to handle all the numbers by saying, basically saying, if my type is satisfying the integral concept or a floating point, then it should be, it's a number, and I want to handle that. The reason I put this aside is because it doesn't have that is not Boolean. And that's a major advantage of using this approach, because by using concepts, then we enable ourselves to get away with having some overlaps between our specializations. We leave it to the compiler to find the right the right specialization that is basically matching the strongest constraint that we have for our type. Now, about strings that I showed you earlier, I was only checking for a string and white strings. Now we can just do this. Again, it's not a perfect code. It's meant to be the simplest way of doing it. Here is how we can handle car arrays and other fixed strings. Now, remember this code snippet where we had this much code just to explain, that our intent is for our type to have a begin and an end. We can simplify that by just saying, by just creating a concept, iterable, that has a begin and an end. In fact, we don't even need to do this because C++20 already has a range library with a range concept. So if our intention is just to iterate over elements, then we don't need to write all that template metaprogramming code. If we wanted to, however, use our own container type, then we can take a look at what the standard considers as a container in a name requirement. And you can check for yourself. There is a long list of requirements that a type should satisfy if it is a container. And in fact, with concepts, it's very easy to express those requirements one by one here. I managed to do that with 3 slides, but if only to just basically say, even the most complex requirements can be easier explained using concepts. Now, someone reading this code would understand our intention. Here is something that we are defining as a requirement, and here is how we are expressing that to the compiler. I emphasize a lot on this intention because I think the most important thing when it comes to writing a library is to make our users or whoever is consuming the library enable them to go read the source code and understand how it works. Because in a lot of cases, we only trust a given library or a given component if you know how it works. Now, the problem with serialization libraries right now is because they want to support older standards, it's very difficult to express those intentions. So we might have been a long-time user of serialization libraries, but never actually dare to look at the source code and how they work. Let's wrap this up by just saying, can we use concepts just like we did for our container, or creating a requires expression for our container to create a requires expression for random data types that we don't know how to handle, the ones that our users should satisfy. So here, take this date class again. For our struct, we can just say we want to handle any type that has a serialized data member that provides our generic value. So in that case, we can do what we did with iterable or container, create a concept, or maybe not even create a concept because it's so simple, and then use basically that as our only specialization that we provide for our users to implement. Notice that unlike other concepts that we did, unlike all the other overloads, this is the code that then we can show to our users and say, take a look at this code. Here's what I want you to do. This is much easier for someone to read and understand than using a partial template specialization sample. Now, here is basically a way for us to make sure that when a user forgets to create basically an overload for our type, they wouldn't get the compile time error that says, I didn't match this concept. It wasn't possible to satisfy this constraint and that and that. We would just basically did what we did with our primary template in our partial specialization technique here with concepts as well. Now, concepts are not the only alternative to partial template specialization. We can use ADL as well. The best way to explain ADL without going into explaining all the rules and when it applies and not is to show you this code example that I really like. It's an end line function that we all know. It's unqualified. We are not specifying what namespace it belongs to. But we are passing the parameter to it, the output stream that it requires. So when a compiler sees this statement, because it's a function call expression, it would start basically checking if we have in our namespace any equivalent end line function. In most cases, we don't have that namespace. So it checks for basically the name. It looks up for a declaration of end line in the namespace of the input parameter that we are passing. In this case, the standard. So it finds our std end line and it would be able to resolve this function call expression. Now, what does this have to do with our type serialization system? The answer is that we can now basically, instead of passing a concept and say, hey, user, satisfy this. You can say, you can just write a member function that takes, that basically has the same name as we want. And then because they pass their type as, its argument, then at compile time, we can find that member function. This is already used in the wild. The best example that I can show is app sales that has basically requires anyone who is trying to support the supported types to create friend functions for operator equality and the app sale hash value. So all we need to do is now to implement these in the namespace of our type. It doesn't have to now be in the namespace of the library, the serialization library, or in this case, the hash library, which is great. And that's why other modern serialization libraries also make use of ADL. Another good example is Nils Lehmann JSON library that basically allows users to just implement the to JSON and from JSON objects for their for their external type. In that case, if I wanted to extend support for the serializable types to my date struct, then I can just basically write this function. And then, in fact, a lot of these serialization libraries provide macros to make it easier for people to express their intent. Now, I take issue with this. I think that when we are using macros, we are hiding actually what the intention of this code is. If I don't know what this macro call is doing, I cannot understand what happens when the compiler sees this. So again, I think the best technique is one that is most applicable to your use cases, but these techniques have different ways of expressing your intents. And I think the best technique is the one that expresses that the most clearly. So if we wanted for our serialization library to use ADL, then we can use somewhat different function, serialize, that takes our context, that enables us to basically create overloads for the set of basic types that we want, and then the external types that we want our users to provide and support. So our users then can write something like this in their as a member function, and that's pretty much all they need to do. It doesn't even need to be a member function, as you saw in the AppSell example. It can just be a friend function that has access to the private members. Okay, so that brings us to the last point in this talk, which is a static reflection. Now, what if we could actually express our intent without providing anything? Isn't it our intention to serialize some type? If I am making use of a serializer library, shouldn't the library be able to just handle the types? Why should I care about implementing my own? Why should it be necessary is better word for it, or better question to ask. Now, take this example again. We are providing a date object as our input parameter, or a map of strings to dates. At the end of the day, it would be nice if the libraries already knew how to handle these types. And it's not too difficult to explain this by saying that all the other languages that do support reflection have actually solved this problem. In fact, that JSON library that I showed you for Java already supports, basically has a default behavior for the types that don't have an explicit type adapter. So that execution path might be slower than usual, but again, it seems like a problem that we can fix. And that's the only reason why I'm including this section, even though it's not part of the standard as we know it today. Now, reflections may not make it to C++ 23, but there are proposals that I recommend that you read just to understand, how it would look like in the future if you were to write a serialization library, or any other type of library that is trying to extend support for external types. Other than these two implementations, the Circle compiler already has support for a separate way of expressing reflections. But the best way to learn about these proposals, or just basically learn about reflections in general, is by the YouTube videos, through the YouTube videos that I've included the names for. But I just want to give you a glimpse of how these works. So let's start with the technical specification draft. That is basically one way of supporting true types. With reflection, our intention is to say, here is the type that I have, or here is, basically, I want to have a way of finding information about that at compile time. And then do basically create patterns that I can then use at runtime. The technical specification draft would basically make use of reflexper operator to promote our type to this meta kind of type, which is a special, basically, which is a type alias that has a kind of meta information. So you can think of it as a meta object. But then, if you look at the code snippet here, it's using type aliases for basically getting information as well. Like in this case, we are creating an alias to the reflexper output, and then getting the name of the, again, type alias that we've defined already to print that name at runtime. In that case, the get type name of a std string would then be the name of the type that the std string actually is, which is basically a string. And then an integer would be expressed as an integer. Notice that right now, if we wanted to do that get type name without reflection, I cannot think of a way of doing that. So now, in addition to just finding type names, we can also find the basically the name of data members, even if they are not public. So in this case, I'm using get accessible data members. Again, I'm defining it as a type alias, and I'm then basically printing the information that I want. Here is some proposal that as far as I know, is not approved yet, but I think would better explain how the reflection TS would work. In this case, I am making basically, I'm creating a to-JSON impl, which is basically taking any type. It doesn't care, we are not creating any constraint for it. But then we say, let's just check the the accessible data members, and then basically print the name and then their values. Of course, this is making use of facilities that are already in the language, like reflexper or unreflexper in this case. In fact, the constexper4 is also new. But at the end, the intention here is to have a way in our basically language to find this information that we otherwise have to rely on our users to support and implement. Here is a separate, basically, way approach. The one that I showed you earlier is true types. This one is basically easier to maybe read, in my opinion, because it's instead of using the type aliases, it's basically using this meta info object. In this case, this is I call it value-based reflection. But I think this term is also used in the proposal for it. Now, of course, what the code snippets that I'm showing here, they are subject to change. The end result that we get might be totally different. But the end goal is that we can implement basically a default behavior for the types that we don't know of, and then have a way of our users basically overriding them by implementing their own. This opens up new opportunities for us in ways of basically expressing the intent when it comes to designing libraries that are supposed to be extensible. Now, again, for a conclusion of this talk, I would say that my goal was not to promote one technique over another. My goal here is to say that when we are designing a library, we need to think of all the techniques that are available to us and make use of them when appropriate. Designing really good libraries requires thinking really well about the expected use cases for it. When do we want our users to do something that we didn't expect? And how do we want our users to be able to express it? I think overall, you can appreciate that the new techniques and methods that are actually being introduced to the language are making it even easier for us to express those intentions. And so I think that we should be optimistic about where the language is going and how we can use the language to build easy to understand software and libraries. That concludes my talk. Thank you so much for being here. And I'd like to thank David Sankel, who's here as well, because of the time that he took speaking with me. Thank you. If there's any question, I'd be happy to answer. Okay, no question? Yes, please.
Just was wondering, Jim was curious about static or reflex expert in the static reflection. I know that that's not in the language right now, but do you know of any sort of like movement for that? Is it going to be is 23 or?
Yes. So the question was, if I know when the reflection, static reflection is going to land. Well, I think the short answer is I don't know. And there are more qualified people who may need to take more time to basically design this better. But as I presented here, there are two proposals right now. There is a reflection TS draft, but there is also this proposal that I showed a simple code snippet for. I think that there are more qualified people in this room who can give better answer about the content of these proposals. But I think the best way of understanding how they work is through reading the proposals. Especially P2320 was the most helpful for me, which is fairly recent as well. Thank you. If there is no other question, I just want to thank you all for being here. And I hope that CppCon was as enjoyable to you as it was for me. Thank you.